So in the first binary that we're gonna work on is crank me. In fact, this is exactly same crank me. For example, and if you type this, it works as expected. But in fact, it has interesting features in it, which we're gonna talk about today. So let's import this in Jydra and see if how this one working. So this is the main logic. Let me interpret one by one. Uh, Thanks to the decompiler output, we don't necessarily start from the instructions as it is. But many of the time, once you understand those logic and figure it out how to debug or how to do the exploitations, you might want to check the original instructions as well. We prefer to see those instructions and the compiler output side by side like this. Once program is launched, it's just printing out those nice banner message and create the prompt. And this was interesting one, right? And if you see this binary, in this function, the function contain, it seems like two local variable is called ivar1 or buffer with the 16 as a size. So in other words, the program is expecting about 16 bytes for the buffer, from the local buffer. But how to interpret this scanf? Any idea? What do you mean by this form as specifier, percentage %s? Okay, someone say wait until null shows up. That's a good guess. But in fact, scanf is actually more than that. And for example, as a user, there's no way you can create the null byte through your terminal, for instance, right? So whenever you type, even if you type just enter, the scanf will stop and read the string for you. So it read until the white spaces show up. That's right. For example, if you provide a string and then string contains some of the white character, such as a space bar. In fact, when we say white space, in fact, it contains many of different characters in ASCII space, which we're going to talk about later, right? But many people consider simple white space the space bar. So, for example, if you provided a, I'll say, let me show you this. If you provide, say, 111, 222, then in fact, this program actually reads just 111. It actually stops at this white space and return 111 as a result, right? But again, we're going to talk about the behavior in detail about scanf. If you go to the tutorial 2, not here. So we have scanf program here. We basically show how the scanf behavior in detail. So we're going to talk about this later whenever necessary for writing the second exploit, right? So, but what if we provide a longer string, which is longer than 16? For example, we are expecting, because in this format specifier, we didn't specify anything about the size or anything about the buffer size, meaning that if user provide more than 16, then it start overriding the rest of the local variable below the buffer, in this case I variable 1. And what's inside, what's below the I variable 1? There is a frame pointer, there's a return address. They will be all overwritten by the user input because of those. So we're going to talk about this. I'm going to show you this, how this one behave in GDB pretty soon, right? So this is what I mean by a stack overflow or stack overflow vulnerability exists in this binary. And then once the user provide the buffer, you compare with this null terminated string, the password. If it match, you print out the password, okay. What's interesting is the second behavior. And then it say no way you can reach because the buffer previously compared with this 2503-81. But after that, we try to compare again in a way that it's the same, then you're gonna print out the key for you. So in other words, according to program logic, there is no way you can trigger this branch, or there's no way you can reach the printf print key in this binary. But because of this buffer overflow in which exists in this line, in fact, we can change the behavior of the program so that we can do something is impossible in this program as well. In this case, like executing this print key functions as well, right? Our plan is to trigger this scanf vulnerability, change the return address accordingly, and manipulate in a way to execute these print key functions. In this case, we're gonna jump to this particular location so that we can push the extra string to the stack and then execute the print key. Okay, so now we have some of the context of the program, right? One of the simple let's first try to trigger the vulnerability and see if what happened. So for example, you can launch the program. What if we provide this live looking string? The program crash, right? Whenever program crash, likely in local your setting based on your setting. But if you're using the VM, the Vagrant image that we are providing, then your system will be set correctly as well to generate the core dump. So in this case, I have located core in this way, in this here, so that if I just type GDB core, pick the latest one and match it with this correct, the binary written in here, that I can easily debug like this. But interestingly, because of the long AAA character, since my stack contain all the AA character, AA basically 61 in ASCII, in hexa representations, and it just contains a bunch of A. Interestingly, my instruction address is also changed to AAAA as well, right? And my stack is pointing to this location, but this location contains a bunch of A, right? And this is exactly what we're gonna exploit today. But unfortunately, if you just provide AAA, and it's hard to understand the behavior, so we can create the pattern. For example, this is one of the tools that we're gonna talk about today. It's called cyclic. It's from the phone tool that we install in our system as well. If you type 10, some of the character, the length, right, as your first parameter, then it will generate the sequence of a character that contain certain pattern, starting from AAAA, the second one starting from BAAA, starting from CAAA. So in other words, if some of the location hit, then we can understand the pattern in a way that we can immediately know the specific locations of the string. So in other words, let's say we create 100, provide to the crank me challenge. And we kind of know that instruction pointer is changed in FAAAA, right? So in other words, what if we create So in this particular location, will be considered the instruction pointer as a result of this execution. This is pretty interesting, but in order to understand what's happening, so let's create a input file and check under GDB. So starting from this week or starting from previous week, we actually are gonna use the phone tool. So if you launch the program in this way, and let's just stop at this scanf and see if what's happening in the system. So copy this location and set the breakpoint on here. And we're gonna launch the program with this input. This input contain in this string. Yeah, we have this input inside this file, and we're gonna run the program with this under input. So because we provide the long input to the program crash before program crash is actually stop in scanf because we set the breakpoint here. So here everything look normal. They're expecting, I'll say, from a string in this case here, right? And this is the beginning of the buffer, right? CD30. And this buffer contain actually some dirty character or dirty data from the previous invocation of the previous use of the stack location. It contains a bunch of stuff, but in fact, it's actually 15 bytes allocated in the system, and starting from here, 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 here. And these are the location of the buffer in the stack. Right below, it contain it seems to contain frame pointer, and then what will be this? Is a return address of this frame. Right? So right after this scanf, see if what's happening in this location. Right? So we're gonna compare exactly like this, right? So let's go to the next one. So we just go to the next instruction after scanf, which means the long input is provided to the program, and we are just return from the scanf as a result. So let's dump the same location. Here, what's interesting is that AAAA, starting from AAAA, we overwrote the frame pointer. We wrote the storage of the previous frame pointer, and also we overwrote the instruction pointer, the return address of this frame. So what if we are actually returning back from this start function, and the program will take this sequence of character as a return address, and instruction pointer will be updated with this value. So in this particular locations, again, when we are returning back from start, in these return instructions, see if what's happening here. So let's copy this one, set the breakpoint, and continue to execute. And we just stop at the leave instruction. In here, we first gonna restore the instruction, the frame pointer with the previously stored value. In this case, interestingly, will be stored with this particular one, right? And stack pointer will be updated with the previous frame pointer, so that top of the stack now pointing to this data. The local frame was cleaned up because of the leave instruction, but top of the stack now contain FAAA. It's pointing to the FAAA data. So what if we return? In fact, it will return to the FAAA as a result, right? Which means this is not the right memory region. And in order to check the memory region, you can type vmmap. Through this vmmap, you can kind of know that what are the legitimate locations in the process right now, which again, our next instruction doesn't fall into this category. So it attempts to change the instruction pointer to FAAA, which is basically non-map region in the memory, so that you got the segmentation fault as a result. But what if we change the instruction pointer in a way that we in a way to point to this location, right here. In fact, GDB inside the GDB, you can actually change the instruction pointer pretty easily. So again, so we assume that we actually override the return address and change the instruction pointer in this way. And can we start executing? Right, we start push this string inside the buffer, inside the stack, which means like 3 tutorial, and we're gonna execute the next function, next instruction. In this case, call printf, which means because after we change the instruction pointer and pointing to this particular location, then you can get the flag as your result. And this is exactly what we're gonna do in first tutorial. Right? So in quick summary, because of the stack overflow vulnerability inside this crank me challenge, we could change the behavior in a way that something impossible happening because of this unintended behavior of exploitation. Because we change the instruction pointer in a way we can invoke the print key function, which is not allowed in the original program, which means as an attacker perspective, now have a capability to change the behavior of the program. And also we can leverage them in a way to get this file on your profit. What should be the corresponding payload to get this behavior happening against this program? So in order to know this, we have to check the corresponding location of FAAA, in this case 20. So after 20 bytes of the program user input, the rest of the 4 bytes will be considered as a return address because of buffer overflow. So in this case, we can actually chain pretty easily, say print out the 20 character. Then we're gonna jump to second one. I think so, yeah. So we're gonna jump to here, right? So we're gonna provide this, but unfortunately, this is not the correct way to represent the integer in the byte, because we have to follow little endian. In this case, 1b, a7. So by providing this e, we just specify that we're gonna interpret this escape character as a result. In other words, a bunch of 20 bytes of A, some uninteresting user input, and then we're going to provide one integer, the address value, starting from 08, 04, 87, and 1B in sequence. If this one was taken as a 4-byte integer or address, will be considered as a 08, 04, 87, and 1B accordingly. What if we provide this all to the crank me challenge? Then, interestingly, once this invalid pathword is printed out, and the program is about to return after processing this, and at this point, now instruction point is set as attacker wanted, and start executing starting from this instruction and start printing out the flag for you, right? So this is how you get the flag in first tutorial. In the second tutorial, we're going to talk about what if crank me challenge doesn't have this print key. And this is a good time to use your shellcode that you prepare. And we're going to talk about this in more programming way, starting from second tutorial.